Hello, fluid enthusiast. Welcome back to part 3 of our mechanical properties of fluids series. Today, we will explore into laminar flow, tube of flow, the equation of continuity, and Bernoulli's theorem in simple terms. Ever witnessed a river flowing smoothly in layers? That is a laminar flow. Join us as we uncover its secrets and explore what it shapes fluid behavior. Curious about flight or fountain dynamics? Bernoulli's theorem has the answers, and we are here to reveal the magic. Ever wondered why planes stay airborne or how chimney smoke does not accumulate in a boiler room? Whether you are preparing for a NEET exam or simply intrigued by fluid mechanics, stick with us. Ready? Let's dive in. Streamline flow. The flow of liquid is said to be steady, streamline, or laminar if every particle of the liquid flows exactly the same path of its preceding particle and has the same velocity of its preceding particle at every point. Let A, B, C be the path of the flow of a liquid, and V1, V2, and V3 be the velocities of the liquid at point A, B, and C respectively. During a streamline flow, all the particles arriving at have the same velocity V1, which is directed along the tangent at the point A. Particle arriving at B will always have the same velocity V2. This V2 may or may not be equal to V1. Similarly, all the particles arriving at point C will always have the same velocity V3. In other words, in the streamline flow of liquid, the velocity of every particle crossing a particular point is the same. The streamline flow is possible only as long as the velocity of a fluid does not exceed a certain value. This limiting value of velocity is called critical velocity. The tube of flow is bounded by streamlines, so that no fluid can flow across the boundaries of the tube of flow, and any fluid that enters at one end must leave at the other end. Turbulent flow. When the velocity of a liquid exceeds the critical velocity, the path and the velocities of the liquid become disorderly. At this stage, the flow loses all its orderliness and is called turbulent flow. Some examples of turbulent flows are: first, after rising a short distance, the smooth column of smoke from an incense stick breaks up into irregular and random patterns. And second example is flash flood. And the second example is the flash flood after heavy rain. Now we will define a critical velocity. The critical velocity of a liquid can be defined as that velocity of the liquid up to which the flow is streamlined and above which its flow becomes turbulent. Now let's obtain the equation for continuity. Consider a non-viscous liquid is streamlined flowing through a tube AB of varying cross-section as shown in figure. Let A1 and A2 be the area of cross-section, V1 and V2 be the velocity of flow of the liquid at A and B respectively. Therefore, volume of a liquid entering per second at A is given by A1 into V1. If ρ is the density of the liquid, the mass of a liquid entering per second at A equals to A1 V1 into ρ. Similarly, mass of a liquid leaving per second at point B equals to A2 V2 into ρ. If there is no loss of a liquid in tube and the flow is steady, then the mass of a liquid entering per second at A equals to mass of a liquid leaving per second at B. Mathematically, it can be expressed as A1 V1 ρ is equal to A2 V2 ρ, or A1 V1 is equal to A2 V2, that is AV is equal to constant. This is called the equation of continuity. From this equation, V is inversely proportional to area of cross-section along a tube of flow. That is, the larger the area of cross-section, the smaller will be the velocity of flow of liquid and vice versa. Now let's derive Bernoulli's equation. Bernoulli's equation states that the work done by all forces acting on a system is equal to the change in kinetic energy of the system. Consider a streamlined flow of a liquid with density ρ through a pipe AB of varying cross-section. Let P1 and P2 represent the pressure and A1 and A2 be the cross-sectional areas at point A and B respectively. The liquid enters through A with a velocity v1 and exits through B with a velocity v2. As the liquid moves from A to B against gravity with B at a higher height than A, an external force is applied to maintain the greater pressure at A, that is P1, compared to pressure at B, that is P2. The mass m of the liquid crossing per second, as per the equation of continuity, is given by A1 V1 ρ is equal to A2 V2 ρ equals to m. Therefore, A1 V1 is equal to A2 V2, implying that the velocity at A is less than the velocity at B due to the larger cross-sectional area at A. The force acting on the liquid at A is P1, A1, and the force acting on the liquid at point B is P2 into A2. The work done per second on the liquid at A is given by P1, A1 into V1, which is equal to P1 into V, and the work done per second on the liquid at point B is given by P2A2 into V2 equals to P into V capital. Here capital V is volume. The net work done per second by pressure energy in moving the liquid from point A to point B is given by P1 V minus P2 V. Now, according to the work energy principle, the work done per second by the pressure energy equals to increase in potential energy plus increase in kinetic energy per second. Therefore, P1 V minus P2 V is equal to into bracket mgh2 minus mgh1 bracket close plus into bracket half of mv2 square minus half of mv1 square bracket close. Now on rearranging the term and dividing the equation by V, we get P1V upon V plus mgh1 upon V plus half of mv1 square divided by V equal to P2V upon V plus mgh2 upon V plus half of mv2 square upon V. Simplifying it further, we get P1 plus rho gh1 plus half of rho v1 square equals to P2 plus rho gh2 plus half of rho v2 square. Since the subscripts 1 and 2 refers to any location on the pipeline, we can write in general P plus rho gh plus half of rho v square is equal to constant. This equation signifies that in an ideal liquid, velocity increases when pressure decreases and vice versa. Here, h is the elevation or the gravitational head, v is the velocity head, and p is the pressure head. Now you can explain why planes stay airborne or how chimney smoke does not accumulate in boiler room. Remember, explanation lies in the statement, in an ideal liquid, velocity increases when pressure decreases. Now let's solve some interesting problems based on the Bernoulli's equation and equation of continuity. Problem 1. A wind with a speed 40 meters per second blow parallel to the roof of a house. The area of the roof is 250 meters square. Assume that the pressure inside the house is atmospheric pressure, the force exerted by the wind on the roof, and the direction of the force will be. Remember, if velocity increases, the pressure decreases. Therefore, the pressure above the roof is less than the pressure inside the room. Now let's apply the Bernoulli's theorem. P1 plus half of rho v1 square equals to P2 plus half of rho v2 square. Here, P1 and P2 are the pressure inside and outside the roof. V1 and V2 are the velocities of the wind inside and outside the roof. Neglect the width of the roof. The pressure difference is P1 minus P2 is equal to half of rho into bracket V2 square minus V1 square bracket close. Therefore, P1 minus P2 is equal to, on substituting the values, we get half into 1 by 2 into bracket 40 square minus 0 bracket close. On simplifying, we get P1 minus P2 is equal to 960. The force acting on the roof is given by F is equal to change in the pressure into A, that is into bracket P1 minus P2 bracket close into A, which is equal to 960 into 250 equal to 2.4 into 10 raised to 5 newtons. As the pressure inside the roof is more than outside, so the force will act in upward direction, and the magnitude of the force is F is equal to 2.4 into 10 raised to 5 newtons. Problem 2. The cylindrical tube of a spray pump has a radius R, one end of which has N fine holes, each of radius R. If the speed of the liquid in the tube is V, asked to calculate the speed of the ejection of the liquid through the small holes. From the equation of continuity, the volume inflow rate is equal to volume outflow rate. Therefore, pi r square into V is equal to n pi small r square into V dash. Here, V dash is the velocity of a liquid coming out through small holes. Simplifying, we get V dash is equal to r square of V upon divided by nr square. As we conclude our exploration of Bernoulli's theorem, our next video will delve into the venturimeters, speed of flux, and more. I am Avinash from www.ginit.com. Before signing off, I did like to request you to like, share, and subscribe to our channel. Continue your exploration of fluid mechanics, and just like how Bernoulli's theorem unveils the mysteries of fluid dynamics, use it to explore your weaknesses and soar high in your NEET exam. Thanks for joining us on this journey. Until next time, happy exploring and best of luck with your studies.